Okay, so since Mathematica was running, I made a little simulation on just using a program called Excel. So here are my dice rolls.
Okay.
Just take random numbers from 1 to 6.
Yep.
Okay. Sorry, this is the average number of numbers I see on each roll. So on this first roll, when I got 5, 1, 5, 1, 5, there's 2 numbers, right?
Okay.
The next one that was 6, 6, 1, 2, 2, there were 3 numbers.
Yep.
This is just counting the numbers of each digit. So there were 2 1s, 3 5s on the first one.
Mm-hmm.
Okay. This part right here, in my 10,000 rolls, I got 6 times where we just saw 1 number. 606 times where we saw 2. 3832 where we saw 3. 4643 where we saw 4, and 913 where we saw 5.
So,
Okay, and the average number of that was 3.5851.
So we did see 4 more than 3.
We did see 4 more than 3. We saw 5 a little bit more than we saw 2.
looks like rolling all of them, all one number is pretty rare.
Very rare, it looks like.
At least
Yeah. But on the other hand, remember we said there were 6 ways to do it out of roughly 8,000 ways? So when we do 10,000 rolls, it's not super surprising to see 6 of them,
Yeah.
right?
Yeah.
All right, so what I'm going to do is let's do some simulations. So the first one, our average number was 3.5851. Do you remember what we got from when we rolled 50 times?
3.64, I think it was.
3.64. So I'm going to write 3.5851 in this cell, and that when I hit return, it'll cause it to run a new simulation. 3.5749. What do you notice that's different about this simulation?
Well, we got like double the amount with 1s.
Okay.
We got less with 2s and 5s.
we still seem to see like 4
4 and 3 stayed pretty consistent.
But
Okay, so even though we got all these additional extra 1s here,
yeah,
our average 3.5749 wasn't really that much different than it was before. 3.5851, 3.5749. Why do you think all those extra 1s didn't shift the average that much?
Well, it went from 6 to 12. And then we're running this 10,000 times.
Okay.
So 12 or so out of 10,000 it'll make that much of a difference.
Okay. All right, here's the next one. 3.5925.
and we only see 10. 10 with 1 now.
All right. What else can you say about this simulation?
Well, it's pretty close to what we had before. With roughly the same number of 2s and 5s. Roughly the same number of everything, actually.
Okay. All right, so let's just go down. 3.5843.
Only 4 with 1 this time.
3.5903. 3.5873. 3.5829.
You wrote 39, not 29.
3.58. Okay, I got to change that to 29. 3.5931.
Might not matter too much.
Well, I'll change it when we finish. So I got to change this one to 29.
Yeah.
Okay, 3.5931, 3.5919, and 3.5908. All right, and this one I got to change to 3.5829. Okay, so there's our 10. And for the average of our 10, we got 3.5873. Is that on screen?
So they all seem to be in like the 3.5.
We're around to that.
Okay.
We got 3.64 for just doing 50, but I guess 10,000 it's going to even out a little bit.
All right. So yeah, why do you think our one? Why do you think our one with just 50 had an answer that was higher than all of our answers here? In fact, we never even saw one that was 3.6. Although this one that's on here right now, 3.599, is pretty close. Why do you think ours with 50 rolls was a little higher?
Well, we didn't see one where we got 1 value.
All right. We didn't see one where we got
Well,
one.
Also,
value.
the smaller sample size.
Okay. So why does a smaller sample size affect?
Well, because then, like, in here, we got, like, if we got, like, 5 2s instead of getting 3 2s, that would affect the outcome more than if we got a couple more 2s in this simulation.
Okay. Yeah, so with larger sample sizes tend to vary from the true mean by a little bit less.
Yeah.
Okay.
So it looks
Although sometimes I have to say you need a very, very large sample size. So you do have to be a little careful. But for something like rolling dice, we can see that 50 gave us pretty good intuition.
We just did it for like 100,000.
10,000, I think.
Right, we did 10,000 10 times. So this is, and there's only about 8,000 combinations anyway. So, you know, with 100,000 here, we're in pretty good shape.
Yeah.
Now, this number over here is the actual true answer that we'll calculate tomorrow, 3.58873.
Yeah.
It looks. I mean, we got 5873 instead of 58873.
Yeah, so are we close?
So we're pretty close.
We're pretty close. All right, so this is a cool problem, and then it's even another really cool thing about this problem is that we can actually solve it exactly
Yeah.
by looking at all the cases, and we'll do that tomorrow.
Okay.
Okay.
All right, high five.